Hi everybody. Today I'm in charge of the Who's Who enzyme, and as you can see, I will talk about carboxylic acid reductases. I guess you have already heard something about them, or at least heard or read the abbreviation, namely CARS. Then these enzymes have been quite popular in the last 5 years. You can see that quite well by just doing a quick search. So I went on SciFinder and I was searching for the term carboxylic acid reductases between 1960 and 2014, and I could get 54 hits, which means one publication per year. Not very much. But when I was searching for the last 5 years, I could get 85 hits, which means 17 publications per year. So a great interest in cars can be observed from different labs reporting new cars and finding applications in synthesis and doing structure analysis. But before talking more about the mechanism and the reactions of these enzymes, let me guide you a little bit through the history of the car with this timeline, with the following timeline. So as you can see, cars are actually not that young. The first biocatalytic transformation of a carboxylic acid to aldehyde was reported by Gross and co-workers in 1959. The same group could isolate and purify the enzyme and show that this enzyme is in need of NADPH and ATP to fully function. So as I said, isolation purification was already done in 68. This timeline is a little bit irritating, and then it says isolation purification 1991. But I could read in the publication that for sure the first purification of a car was done years before. Anyway, let's come to the next milestone, which was in 2004, where the first amine sequence of a car from a bacterial source, namely Nocardia iovensis, was elucidated. Then, 3 years later, in 2007, a researcher found out that cars require post-translational modification of a zero at position 689. And just 3 years ago, the first crystal structure of a carboxylic acid from Mycobacterium marinum was published. Most of the core sequences have been found in bacteria and fungi, although there are reports that this reaction can be even observed in plants too. But core sequences so far have been only reported from fungi and bacteria. So a review from 2018 showed that till then 24 cores from bacterial and 15 from fungi were characterized so far. Cores are quite complex enzymes. Then they consist of multi-domains, which means that an approximate weight of such an enzyme is between 120 and 130 kilodaltons. And in order to have a fully functional enzyme, the following ingredients are important, which are magnesium ions, ATP, as well as NADPH, and the already mentioned post-translational modification of a serine at a position 689. Cars are historically named arylaldehydes. Dehydrogenases, which indicates selectivity for aromatic substrates, but this is not valid anymore. And these enzymes are highly promiscuous. In the last years, people reported a lot of different substrates which were accepted by cars. For example, short chain medium aliphatic acids or aromatic and heteroaromatic acids, as well as polycyclic acids like this indole derivative. Yeah, it was. It was observed that only a car from the organism Signiliparo rugosus could reduce nitrogen-substituted benzoic acids. But for all cars, so far some limitation can be observed. One limitation is that polar groups adjacent to the carboxylic acid moiety are not working as substrates, and in vivo approaches, aldehydes are usually reduced to the alcohol because aldehydes are generally toxic for cells, and in vivo approaches are quite preferred because of the need of NADPH and ATP. Some strain engineering has been already done here, but this is so far not an overall solution, which means there's still room for improvement. Now let's go to the biocatalytic mechanism of this enzyme. So if you look at the scheme, the whole reaction looks quite simple. We just need a carboxylic acid, our enzyme, we put in cofactors ADP and ADPH, and we get our aldehyde. But actually, to perform this kind of reaction, that enzyme needs 3 different domains. So the first domain is called the A domain, where the adenylation step is performed. The second one is the T domain, where the transtyrylation is performed, and the last domain, the R domain, is finally there to reduce the intermediate to finally get our aldehyde. So, according to the latest publications, following core mechanism is proposed. So, in the first step, the substrate enters the active site and attacks the alpha phosphate of the ATP in order to become an activated AMP ester at the expense of ATP. In the next step, the activated ester gets then transesterificated by the thiol from the post-modified serine at the position 689. AMP is released and the evolved thioester is covalently bound to the post-modified amino acid serine. The phosphopentoyl serine serves as a swing arm to bring the intermediate from one domain to the other, namely the R domain. In the R domain, the thioester gets finally reduced by NADPH and the product is released. But not only the mechanism gets researchers very excited, the needed reaction conditions do it as well. Then to perform this kind of reaction, we only need 30 degrees, work in an aqueous medium at a neutral pH, namely 7.5. Due to time reasons, I will just show one well-studied application of a car, namely the synthesis of the aldehyde vanillin. The synthesis of this molecule is especially interesting because it's used in food and in the fragrance industry. And last year, 16,000 tons were produced, and the biocatalytic production of it can be marked as natural, which increased the price 250 times more times greater than the synthetic vanillin. So a promising biocatalytic way is shown in this figure. Here we start from glucose in order to come to this acid. Then, through the help of a dehydrogenase, namely ASBF, the ketone moiety gets reduced to the following acid. The acid is then reduced by a carboxylic acid reductase in order to get an aldehyde. But to get vanillin, we still need to methylate the OH at the 3 position. The methylation can happen before or after the core attacks. It accepts both substrates. As you may know, aldehydes, like vanillin, are toxic to cells, and the whole approach that I just showed to you is done actually in a whole cell system. So in order to increase the yield of the vanillin, an additional step was introduced, namely the glycosylation of the vanillin to vanillin beta-D-glucosides. The attentive observer will realize that after the glycosylation step, we still have an aldehyde. But it seems like that this molecule is less toxic than the vanillin itself. So the shown reaction here is typically done by cars. But however, Fletch and co-workers could show an untypical car reaction, namely the amidation of a carboxylic acid. In order to achieve this, they performed two different ways. So one way was to mutate the post-modified serine to aniline, and just to cut off the R domain where the whole reduction step is performed. And both ways were actually working for them. So in order to show the success of the performed ways, they used the substrates to make elliptimide, which is a medication against epilepsy. And as you can see, the only difference in these two different ways was in the yield. So the truncated core got only a conversion of 60%, while the mutated one could even yield a conversion of 79%. So although cars are very promising enzymes, properties such as thermostability or high activities for a particular substrate still needs to be improved. And one way to improve enzymes is the use of direct evolution. But although direct evolution is used by many groups and is already well implemented, it's still not easy, even if when we use like simple enzymes. And it becomes even a greater challenge if you want to do it on multi-domain enzymes like cars. But luckily, just recently, Winkler and co-workers developed a UV and fluorescence-based high-throughput assay for aldehyde quantification in the presence of microbial cells. And this method allows the detection and quantification of aldehyde formation even in the presence of resting E. coli cells. So the assay works in a way that we express our enzyme in E. coli. We put our substrate inside, namely a carboxylic acid, and when the enzyme does a job and reduces it to aldehyde, the developed assay compound, namely ABAO, will just react to it and produce a dehydroquinozoline derivative, which can be then detected by UV. So, showing you all of this information, we could see that just in a short amount of time, a lot of things have been done and discovered for carboxylic acid reductases. So soon, for sure, more industrial application will be investigated, especially because aldehydes are used in the fragrance and food industry. More and more cars will be discovered, and just a small amount have been characterized so far. And on top, there's still room for improvement for the reaction setup. Then reactions still can't be fully exploited. For example, because the activity towards spherical demanding substrates is very poor, the catalytic efficiency is not very high, and although in vivo systems are preferred because of the use of ATP and NADPH, the theoretical perfect aldehyde levels are diminished by side reactions. As I already told you, aldehydes are toxic to the cells, and therefore it will try to get rid of the aldehydes by, for example, reducing it to the alcohol. Recycling systems have been implemented already, but could still be improved. Especially interesting in order to get rid of the in vivo systems and the problem of the toxicity of the aldehyde, and to use substrates that can't overcome the cell wall and therefore to grow the substrate scope. I hope that I could show, or that I could give you a good overview about carboxylic acid reductases, especially in the last years. And thank you very much for your attention. If you have any questions, feel free to ask me.